To cement your linked list mastery, try these 5 classic follow-ups next. Reverse linked list 2 builds on today's pattern, challenging you to reverse only a section of the list. Palindrome linked list requires checking if a list reads the same forward and backward, which often involves reversing part of it. Merge 2 sorted lists is perfect for practicing pointer updates as you combine 2 lists into one. Let's break down the remove Nth node from end of list problem. You're given the head of a singly linked list and an integer n. You need to remove the Nth node from the end of the list. As shown in the image, if the list is 1, 2, 3, 4, 5 and n equals 2, the node with value 4 should be deleted. The output should be 1, 2, 3, 5. Let's assess what's tricky here. A brute force way is to count the nodes, then walk to the node just before the one to remove. But that takes 2 passes. Interviewers want a slick, 1-pass solution. The classic trick is to use 2 pointers, fast and slow. Now, let's structure our approach. Create a dummy node pointing to head to handle edge cases easily. Move the fast pointer n steps ahead. Move both fast and slow pointers until fast reaches the end. Skip the Nth node from end by setting slow.next equals slow.next.next. Return dummy.next as the new head. Now let's solve solution 1, removing the nth from the end of a linked list using a 2-pass approach. We'll see how to compute the length first, then remove the target node step by step. Time complexity is O(n), where n is the number of nodes in the linked list. We traverse the list twice, once to count nodes, once to remove the target. The idea: first pass, compute the length of the linked list. Second pass, go to the node just before the target node, length, n. Adjust pointers to skip over the nth from the end. Think of it like counting how many people are in line, then removing the person at a specific position from the end. Line-by-line explanation of the code, we define a class solution to hold our method. This function takes the head of a linked list and an integer n, and removes the nth node from the end. Create a dummy node pointing to the head. This simplifies edge cases like removing the first node. Length will count the total nodes. Cur is used to traverse the list starting at the head. Loop through the list to count its length. For each node, increment length and move cur forward. Reset cur to the dummy node for the second pass. Move cur to the node just before the target node. Length, n steps from dummy gets us there. Skip over the target node by adjusting pointers. This effectively removes it from the list. Return the new head of the linked list, starting after the dummy node. And that's how this algorithm works. It first counts the length of the list, then locates the node just before the target, and finally removes it by adjusting pointers. Efficient, simple, and elegant. Time complexity is O(n), 2 passes, but linear overall. Space complexity is O(1), no extra data structures used. Using a dummy node handles edge cases like removing the first node. Simple and intuitive 2-pass solution. We're testing our function that removes the nth node from the end of a linked list. For the input head equals 1, 2, 3, 4, 5, and n equals 2, we want to remove the second to last node, which is 4. The solution works by getting the list length, finding the node right before the one to remove, and skipping over it. This gives us the final list, 1, 2, 3, 5. The function removes the correct node and keeps the list structure intact. This solution removes the nth node from the end of a linked list in 1 pass using 2 pointers. Instead of calculating the length first, we move 1 pointer ahead and then move both pointers together to locate the target node efficiently. Time complexity is O(n), where n is the number of nodes in the linked list. Each node is visited at most once, giving linear time. Define a class solution and the function remove Nth from end. Start with a dummy node pointing to the head. This helps handle edge cases, like removing the first node. Set both slow and fast pointers to the dummy node. Slow will eventually stop before the node to remove, and fast helps locate that spot. Move the fast pointer n+1 steps ahead. This ensures the gap between slow and fast is exactly n nodes, so when fast reaches the end, slow is right before the target. Move both slow and fast 1 step at a time until fast reaches the end. Slow stops just before the node we want to remove. Skip over the target node by pointing slow dot next to the node after it. This effectively removes the nth node from the end. Return the head of the modified list, which is dummy.next. This also handles cases where the original head was removed. Using a dummy node simplifies edge cases. Only 1 pass through the list is needed, and 2 pointers maintain the exact gap needed to find the nth node from the end. Now let's see how our solution works on a simple test case. For the input head equals 1, and n equals 1, We want to remove the only node in the list. The algorithm uses 2 pointers. Fast moves ahead by n+1 steps, so slow ends up right before the node we need to remove. Since this list has just one node, slow stays at the dummy node, and removing slow.next gives us an empty list. And that's exactly what the output shows, an empty list. This confirms our implementation works correctly, even for edge cases where the entire list is removed. Breakdown recap. Conceptually, the task is to remove the nth node from the end of a singly linked list. It's about navigating the list efficiently without counting nodes multiple times or using extra space. Assess recap. A brute force approach would be 2 passes. Count nodes, then locate the node to remove. The optimal interview-friendly approach uses 2 pointers, fast and slow, to accomplish this in 1 pass. This technique allows you to reach the target node directly while maintaining ON time and O1 space. Structure recap. Here's the plan. Start with a dummy node pointing to the head to handle edge cases. Move the fast pointer n steps ahead. Move both fast and slow pointers together until fast reaches the end. Slow will then be just before the target node, so skip it by adjusting pointers. Return the new head from dummy.next. Implement recap. We implemented the 2-pointer approach with a dummy node, carefully moving fast and slow until the correct node could be removed. Running it on LeetCode, the code executed cleanly without errors. Check recap. We verified the logic for various list lengths and positions of n. The solution consistently removed the correct node and returned the updated list. It runs in ON time with O1 extra space. Closing insight. The key takeaway? 2 pointers and a dummy node make 1-pass operations both safe and elegant. Mastering this technique ensures you can handle a wide range of linked list challenges confidently.